Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine for a second that you are, millions of miles away from Earth.
Right.
Just hurtling through the absolute pitch black, freezing void of deep space. Everything is going perfectly according to plan. And then suddenly something completely unexpected happens.
Always does.
Exactly. Like maybe a piece of debris strikes the hull, or an unprecedented solar flare washes over the ship, or, a vital thruster just suddenly misfires.
Oh, that's bad.
Yeah, it's bad. Alarms are going off. You desperately need a solution. But here is the terrifying reality. Because of the sheer vastness of space, there is this massive communication delay.
Massive.
Right. A distress signal sent to Earth might take, say, 20 minutes just to get there. And then another 20 minutes for any kind of response to actually come back.
Yeah, and by the time Earth even knows you're in trouble, the mission could already be totally lost.
Completely lost. The spacecraft just has to figure it out entirely on its own.
It's basically the ultimate locked room puzzle.
Mm-hmm.
But, the room is traveling at thousands of miles an hour through the most hostile environment imaginable.
Yeah.
When a mission is that far out, autonomy isn't just some, futuristic luxury. It is a baseline requirement for survival. You simply cannot wait for a human sitting at a desk in a control room on Earth to just push a button.
So to figure out how we survive that scenario, today we are talking about a really monumental technological leap from NASA's Jet Propulsion Laboratory. We're looking at their new High Performance Spaceflight Computing processor.
Like a game changer.
It really is. We are talking about a revolutionary AI space chip designed to let spacecraft literally think for themselves. So, okay, let's unpack this. Because to truly appreciate how transformative this piece of hardware is, we really need to understand the reality of how spaceflight computing currently operates. And frankly, the current state of technology up there might surprise a lot of people.
Oh, absolutely. Because, people naturally assume that since we are sending these incredibly sophisticated billion-dollar machines out into the cosmos, they must be running on the absolute bleeding edge of computer processing.
Right, like they've got the best tech available.
Exactly. You might picture quantum computers, or at least processors that are vastly superior to the laptops sitting on our desks. But the truth is entirely the opposite. Current space missions rely on computing cores that are heavily outdated by earthly standards.
Which seems completely counterintuitive until you look at the extreme bottleneck of space exploration.
Right.
The environment beyond our atmosphere is just utterly brutal on electronics. We're talking about intense electromagnetic radiation constantly bathing the solar system.
And the temperature swings.
Yes. Dramatic temperature fluctuations swinging from hundreds of degrees above zero to hundreds of degrees below, sometimes in a matter of, minutes.
Yeah. But, the real enemy of modern computing out there is the high-energy particles.
Explain that a bit more. What kind of particles?
Well, those particles are essentially the absolute bane of a spaceflight engineer's existence. We're talking about cosmic rays. They're basically atomic nuclei traveling at a significant fraction of the speed of light, coming from the sun and deep space.
Okay.
And when one of these particles strikes a delicate modern computer chip, it does something entirely disruptive. It doesn't necessarily leave a physical bullet hole.
Right.
Instead, it dumps a massive amount of kinetic energy directly into the silicon, and that knocks electrons completely out of their atoms.
Okay, I want to pause here to really visualize this. You're saying this invisible microscopic collision creates a literal burst of electrical charge inside the computer processor.
Exactly. That sudden burst of stray electrical charge can actually trick a delicate transistor into changing its state. So it flips a 0 to a 1, or a 1 to a 0.
Oh, wow.
Yeah, we call this a single event upset, or a bit flip. And when that happens, the computer might suddenly calculate the wrong navigational trajectory, or an entire subsystem just gets confused.
That's terrifying.
It is. So when a current spacecraft detects this kind of cascade error, it is programmed to immediately panic and force itself into what we call safe mode.
And safe mode is basically the spacecraft curling into a defensive ball to protect itself, right?
Yeah, that's exactly what it is.
It temporarily shuts down all non-essential systems. The science instruments turn off, the cameras power down, and the entire multi-billion-dollar machine just goes completely dormant.
It just floats there.
Right. Just floating, waiting for human engineers back on Earth to manually analyze the telemetry, find the flipped bit, and slowly coax the system back to life.
And during that downtime, the spacecraft is effectively blind and paralyzed. So historically, NASA has deliberately made a really severe trade-off. To avoid those constant, terrifying system crashes, they use older, incredibly durable chips.
Older chips?
Yeah, those legacy chips have physically larger transistors. And because they are larger, it requires significantly more energy to flip their state from a 0 to a 1. So they are highly resistant to those cosmic ray strikes.
So it sounds like we're sending these incredibly vital missions into the void running on the equivalent of like a 1990s brick phone.
Basically, yeah.
And we use them just because we know the screen won't crack, even though the mission really demands a modern smartphone.
That's a perfect analogy. And that trade-off has been completely necessary. I mean, a cutting-edge, ridiculously fast, modern computer is utterly useless if a single solar flare fries its microscopic circuits on day 2 of a 10-year mission.
That's fair.
Surviving the environment is the non-negotiable baseline. Everything else, processing speed, artificial intelligence, complex data analysis, that has traditionally been treated as a secondary luxury.
Okay, but I am trying to reason through this engineering problem here.
Sure.
If we need modern computing power, but the microscopic transistors are too fragile, why not just take a powerful modern chip out of a high-end server, put it inside a really thick lead box to block the radiation, and just send that into space? Why do we need to invent a completely new chip from scratch?
Well, that immediately runs into the tyranny of the rocket equation.
Wait.
Exactly. In spaceflight, weight is your absolute worst enemy. Every single ounce you send into orbit costs thousands of dollars in rocket fuel. A thick lead box heavy enough to stop high-energy cosmic rays would be, well, impossibly massive for a modern deep space probe.
That makes sense.
And add to that, heavy metal shielding can sometimes cause secondary radiation scatter.
Wait, what does that mean?
So the cosmic ray hits the lead, and it shatters, creating this sort of shotgun blast of secondary particles that still hit the computer.
Oh, wow. So the armor actually makes it worse, in a way.
Sometimes.
Yeah.
You cannot just armor a regular chip. You have to build the resilience directly into the silicon architecture itself.
Which bridges us directly to NASA's game-changing development program down at the Langley Research Center. They realized we are, hitting a wall with the brick phone approach.
Right.
If we want autonomous spacecraft or vastly faster onboard scientific analysis, we need high performance without sacrificing that baseline of survival. And the result of that effort is the High Performance Spaceflight Computing processor.
The HPSC.
Yeah. And the physical form factor of this hardware is surprising. It is a system on a chip, or small enough to fit completely in the palm of your hand.
The system on a chip architecture is really vital here. Traditionally, a computer uses a large motherboard. You have your central processing unit in one corner, your memory in another, and your networking interface is somewhere else.
Right, spread out.
Yeah, and data has to physically travel across wires between those components, which takes time and energy. And SoC combines all of those essential components into a single, highly integrated unit. You have your CPUs, your computational offloads, advanced networking, and memory interfaces all stacked together on one tiny piece of silicon.
Wait, you mentioned computational offloads. I want to clarify that before we move on.
Yeah.
What does an offload actually do in this context?
Good question. Think of the main CPU as the head chef in a busy kitchen. If the head chef has to chop every single onion and wash every single dish, the actual complex cooking just grinds to a halt. A computational offload is like hiring specialized prep cooks. It is a dedicated piece of hardware on the chip designed to handle one specific, highly intensive task.
Like what?
Like crunching heavy math for navigation or processing images from a camera. It offloads that burden from the main CPU, allowing the entire chip to run vastly faster and more efficiently.
I appreciate that clarity. But I have to push back on the novelty of this hardware for a second.
Oh.
Yeah, my tablet and my smartphone use an SoC right now. I mean, that is how we get consumer devices to be so remarkably thin. What makes NASA's version a technological breakthrough if I literally have an OC sitting in my pocket right now?
Well, the chip in your pocket operates in an incredibly cozy environment. It enjoys the luxury of Earth's magnetic field, protecting it from cosmic radiation, and it just sits at a comfortable room temperature.
That's true.
NASA's version is radiation hardened from the ground up, utilizing completely different engineering principles.
So how exactly do they harden it without using that heavy lead box we talked about earlier?
One of the most fascinating mechanisms is called triple modular redundancy.
Triple modular redundancy.
Yes. Instead of having one microscopic circuit do a calculation, they build 3 identical circuits directly into the chip to do the exact same math simultaneously.
Wait, all 3 at the same time?
Simultaneously. And at the end of the calculation, they essentially vote on the answer.
Oh, that's brilliant.
Right. If a cosmic ray strikes one of the circuits and flips a bit, causing it to output a wrong answer, the other 2 circuits will just outvote it. The chip instantly recognizes the error, ignores the glitch, and keeps functioning perfectly.
Wow.
They also use insulating layers in the silicon itself, often called silicon on insulator, to physically prevent that stray electrical charge from jumping between components and short-circuiting the system.
So they're essentially weaving fault tolerance into the actual logic of the machine.
Exactly.
And here is where the leap in capabilities gets really staggering. The design goal for this project was to deliver up to 100 times the computing power of the spaceflight computers we are currently using.
100 times is already huge.
Yeah, but when they started putting the prototypes together and looking at the early data, they reported it is operating at performance levels roughly 500 times greater than current radiation-hardened chips.
A 500-fold increase just completely alters what a spacecraft can accomplish.
How do we properly visualize an increase of 500 times? Because people often use the cliche of trading a bicycle for a fighter jet, but that doesn't really capture the mechanics of data processing.
No, it doesn't. A better way to look at it is through parallel processing.
Mm-hmm.
Imagine you were trying to find one specific quote hidden somewhere inside a massive library.
Okay.
The current space chips are like having a single librarian who has to read every single book, page by page, one after the other. It is reliable, but painfully slow.
Right.
This new chip is the equivalent of unleashing 500 highly trained librarians to scan the entire library simultaneously. Tasks that used to take hours can now be completed in a fraction of a second.
Of course, you don't just build a 500 librarian superchip, look at the paper specs, and bolt it onto a rocket. You have to definitively prove it can survive the environment.
Oh, absolutely.
Which brings us to the grueling testing phase happening right now at NASA's Jet Propulsion Laboratory, JPL, down in Southern California.
Yeah, Jim Butler is the project manager overseeing this at JPL, and his team's entire job is to literally torture this hardware.
Torture is the right word.
They began testing in February 2026, and they are putting these chips through an absolute ringer. I mean, they are placing them in thermal vacuum chambers that simulate the freezing, airless void of space, baking them to extreme temperatures and bombarding them with heavy radiation to see if that triple modular redundancy actually holds up.
And beyond the environmental torture, they're simulating the immense computational stress of an actual mission. Let's talk about the specific high-fidelity landing scenarios JPL is using. Because what exactly happens computationally when a machine tries to land on another planet like Mars?
Well, a planetary landing is often referred to as 7 minutes of terror.
Right.
The spacecraft is hitting the Martian atmosphere at thousands of miles an hour. In a span of just a few minutes, it has to deploy supersonic parachutes, jettison heat shields, fire retro rockets, and simultaneously use optical cameras, radar, and LiDAR to rapidly scan the terrain below to avoid crashing into a crater or a boulder.
The sheer volume of raw data flooding into the computer in those few seconds must be, well, astronomical.
Oh, it is. And if the processor lags for even a fraction of a second, the mission becomes a crater.
Wow.
Which is precisely why JPL is using these specific scenarios. They are digitally throwing the entire tidal wave of simulated landing sensor data at this palm-sized processor, forcing it to calculate real-time hazard avoidance.
While they're torturing it physically, too.
Right, while simultaneously shaking it violently on acoustic vibration tables that mimic the destructive roar of a rocket launch. They want to see if the chip misses a single clock cycle under the most extreme physical and computational stress imaginable.
So they're essentially forcing a supercomputer to run a marathon while
locked inside a microwave, yeah.
Right, a microwave being shaken in a paint mixer just to make sure it doesn't blink during a planetary landing.
Exactly. And the testing campaign is proving that this chip handles the load flawlessly. It is calculating precision landing adjustments entirely on its own without relying on an earthbound supercomputer.
That's incredible. And when the team at JPL initially kicked off this rigorous testing protocol, they sent an internal email to mark the occasion. The subject line was simply, "Hello, Universe."
I love that. What's fascinating here is that phrase, "Hello, Universe," is a brilliant subtle nod to the history of computer science.
Oh, like hello world.
Yes. Whenever a student learns to write code, the very first program they are taught simply prints the words "Hello World" on the terminal screen. It is the universal sign of a system waking up.
Right.
By expanding it to Hello Universe, the engineers are acknowledging the gravity of what they have built. This is the moment. Robust, modern computing architecture finally scales to the demands of the cosmos.
It is a massive engineering triumph. But NASA is not doing this in a vacuum. Back in 2022, JPL selected an Arizona-based company, Microchip Technology, Inc., as their commercial partner.
Yeah, they actually co-funded the research.
Right. They co-funded the research and development work on the processor, which opens up a vital question. How exactly does this unprecedented processing power fundamentally change how we explore?
Well, the answer really lies in localized artificial intelligence. Until now, utilizing AI in deep space was nearly impossible because machine learning algorithms require massive amounts of rapid computation.
The kind of computation that would instantly overwhelm a legacy spaceship.
Exactly. But with this new processor, spacecraft can finally run complex AI models locally on the fly.
Which brings us full circle to the disaster scenario we discussed at the beginning of the show. You are millions of miles away, debris strikes the hull, and Earth is a 40-minute round-trip message away. With onboard AI, the spacecraft analyzes the sensor data the millisecond the impact happens. It instantly realizes a thruster is failing, calculates a new power distribution to compensate, autonomously fires secondary rockets to stabilize the spin, and keeps the mission alive, all in real time.
It's amazing. And beyond just disaster mitigation, consider what this means for actual scientific discovery. Deep space probes collect staggering amounts of raw data.
Oh, yeah.
Think of a probe orbiting Jupiter looking for a specific split-second ice geyser erupting on the moon Europa. Currently, a probe has to take thousands of high-resolution images and slowly trickle all of that raw data back to Earth over the Deep Space Network.
And the Deep Space Network is incredibly reliable, but it has severe bandwidth limitations.
Severe.
Sending gigabytes of raw photos from Jupiter is like trying to download a 4K movie over a 1990s dial-up modem.
Yes.
It just takes forever, and humans on Earth have to manually sift through thousands of photos of empty space just to find the one image of the geyser.
But with this powerful new processor, the onboard AI serves as an intelligent curator. It pre-processes all the data right there in Jupiter's orbit.
Okay.
The AI looks at the 1,000 pictures, instantly identifies the one single image that captures the anomaly, discards the useless data, and only transmits that one highly valuable compressed insight back to Earth.
That's incredible.
It turns a dial-up connection into a pipeline of pure scientific discovery. And we are looking at deploying this in Earth orbiters, tracking rapid climate change, planetary rovers navigating the chaotic surface of Mars, and critically, keeping living astronauts safe during crewed missions to the moon where split-second life support decisions are mandatory.
Now, I want to pivot here and ask the really vital grounding question. It is amazing that a probe near Jupiter will soon be able to think for itself, and it is incredible that astronauts will have vastly better life support computers.
Right.
But how does this commercial partnership with Microchip Technology benefit you, the listener, driving to work right now? What is the practical earthly application of this highly specific space hardware?
This is where we see the historical pattern of space exploration accelerating terrestrial technology. Think about the engineering paradox. NASA forced Microchip Technology to solve here.
Okay.
Build a processor capable of running advanced AI and processing immense amounts of sensor data instantly, but make it incredibly compact, energy efficient, and essentially indestructible against systemic failure.
So they demanded indestructible AI computing.
Indestructible. Now
Wow.
take that exact same processor architecture and install it into a commercial airplane.
Oh, wow.
Yeah. The aviation industry requires fault-tolerant computing, where an in-flight system failure is simply not an option. Or, to bring it directly to your morning commute, consider the chips powering autonomous vehicles.
That makes perfect sense. A self-driving car is basically a terrestrial spacecraft navigating dynamic hazards.
Exactly. The chip sitting behind the dashboard of an autonomous car driving you to work relies on a massive influx of data from cameras, LiDAR, and radar to navigate unpredictable city streets safely. While it doesn't face the extreme cosmic radiation of deep space, it absolutely requires that same fault tolerance. If a component glitches while the car is traveling 70 miles an hour down a highway, it cannot freeze or enter a safe mode.
No, definitely not.
It needs to make a life or death decision in a fraction of a second without waiting for a slow cellular cloud connection. By partnering with NASA to build the ultimate autonomous space brain, Microchip has inadvertently designed the perfect processor for high-stakes earthly industries.
So the technological foundation that will land the next advanced rover on Mars is the exact same architecture that could eventually be making your drive to the grocery store infinitely safer.
It's all connected.
It really showcases the ultimate return on investment for pushing the boundaries of engineering. We set out today to understand how this new chip works, and the journey reveals that we are watching the evolution of our space program happen right now in real time.
We really are.
We are officially graduating from sending highly durable but ultimately remote-controlled calculators out into the dark. We are moving toward deploying brilliant, palm-sized brains that can pilot themselves through the void, flawlessly land on alien worlds, and accelerate our understanding of the universe by analyzing the cosmos entirely on their own.
It is a profound shift in how we interact with the universe.
Yeah.
And, leaves you with something deeply fascinating to consider.
What's that?
Well, for decades, our spacecraft has strictly been our tools. They're incredibly complex tools, certainly, but ultimately, they merely executed the exact commands we sent them from Earth.
Right.
But if these new AI processors allow spacecraft to process massive amounts of environmental data, instantly react to the unexpected, and make their own critical decisions millions of miles away from human intervention, well, at what point do they stop being just our tools and start becoming the actual explorers?
Wow. That is a thought that will stick with me for a long time. The next time you look up at the night sky, remember that very soon there won't just be machines up there waiting for our instructions. There will be brilliant, palm-sized brains thinking, reacting, and figuring out the vast, unforgiving void on their own. Thank you so much for joining us for this conversation. Keep looking up, keep asking questions, and we will catch you next time.